My name is Zheng Wang. So I'm a student from IC department. So I'll give this guest lecture on ferroelectric memory. So this is today's outline. I'll first talk about the history of ferroelectrics. Then I'll give a brief review on some basic electrostatics. And then I'll talk about ferroelectric materials and devices and their issues. So this slide summarizes the short history of ferroelectrics. So there are three important time or period. The first one is the discovery of ferroelectricity in 1920 in the Rochelle South. The second important period is the ferroelectricity in perovskite materials from 1940 to 1950. Perovskite materials lead to a lot of important applications such as transducers, energy harvesting devices, memories, and sensors. And the last one is the ferroelectricity in soft Hafnium materials, because Hafnium oxide is a CMOS compatible materials and has already been used in the semiconductor industry. So this opens a new area for ferroelectricity because we can now make transistors with that. So now I'll start a brief review of some basic electrostatics. So you've perhaps also learned this before. So we have two charges here. So one is negative and one is positive. So we can form a dipole. So the dipole moment is pointing from the negative to the positive charge, and with a magnitude of Q times S. In dielectric materials, the dipoles are aligned with the external electric field, and polarization P is just N times this dipole moment, where N is the number of dipoles per unit volume. And this polarization P is also related to the electric field by this equation here. If this dielectric is linear and homogeneous. So how's the surface charge relates to the polarization? So if you look at this red box, so inside this box is charge neutral. So there is a net negative charge on this left surface, and there's a net positive charge on this right surface. So the surface charge density is just this polarization P. So how do we derive this? So if you look at this box, the volume, so this area times D gives you the volume, and times N gives you the total number of dipoles in this volume. So times Q, you get the total charge. Then you divide it by area, you get the surface charge density, which turns out to be this P value here. So if it's negative side, you get negative P. So the displacement field, by definition, is epsilon times E plus this P. And this 1 plus chi gives you the relative permittivity of the material. So any questions at this point? So now I'll start talking about materials. And, so we are looking at this subset of dielectric called ferroelectrics. This is a very small subset of materials. So for a material to be ferroelectric, it has also to be piezoelectric and pyroelectric. So anyone knows what piezoelectric and pyroelectric is? Okay, so I'll explain this. So for piezoelectric, you apply external stress to the material, so there's current generated. So the pyroelectric means you heat or cool the material, so there's voltage generated. So the definition for ferroelectricity is the spontaneous polarization can be reversed by external electric field. So if you look at here,
can you repeat the definitions, please?
For the pyroelectric and the so for the piezoelectric, you apply external stress, so there's current generated in the material. So for pyroelectric, you heat or cool the material, so there's a voltage generated. So in the case of ferroelectric, if you have external electric field. In this case, the electric field is pointing downward, so your dipole is pointing downward as well. So if you flip the electric field, so the dipole will also flip in the material. So now I'm introducing one of the important ferroelectric material called the PZT. So above the Curie temperature, so this PZT is in this cubic nonpolar phase. So you have this parabolic shape energy landscape. So there's a global minima here, so this is stable. So if you go below the Curie temperature, the energy landscape is double wave energy landscape. So there are two minimas here. So in this case, you can switch the polarization. So what happens is that once you apply the electric field, the center atom in this case is either titanium or zirconium. So you can, with the electric field, you can move this up and down to change the polarization value. So this graph shows the typical polarization versus electric field looks like. So it has a counterclockwise hysteresis. So at zero electric field, you have this double wave energy landscape. So there's two minimas. So at this point, you may be at here, and at this point, the p-value is at this minima here. So if you apply electric field, so the energy landscape will get tilted. So if the electric field is large enough, so this minima will disappear. So this ball will move to this global minima. So that's how the switching occurs in the ferroelectrics. Microscopically, you can think about this switching as domain switching inside the material. So as this states, the polarization is pointing downward. If you apply the electric field, some of the domain may point upward. So if you further increase, more domains are flipped. And if it's large enough, the entire domain is flipped. Now the polarization is pointing upward. So here I'm showing the PFM result of this material. So as you can see here, initially this domain is pointing upward, and you can see the phase is red. Then after some time, you can see some red dot here. So that means some of the domain get flipped, and with time increases, you can see more domains are flipped. Now you can see more yellow color here. So after 1 second, the entire domain is flipped. So any questions?
So does the material structure really change during different polarization?
Can you speak louder?
Does the material structures for the different polarization does change inside the
so the phase is changed, but you see this atom is moving up and down for different polarization value.
So actually just the middle atoms?
Yeah, middle atom, this titanium or zirconium atom will move up and down, depends on the electric field. So this is pointing down, you move at top, it's up when the P is up. But still it's still in the tetragonal phase.
Yes, does the phase correspond to the polarity of the polarization, and the amplitude correspond to the amplitude of the polarization? Amplitude.
So phase corresponds to the direction of the polarization. Yeah. So, but I don't know like what amplitude tells you in this case. So to model this, we first think about this phenomenological model by Landau. Okay.
Actually, to answer that, I think the amplitude corresponds to the deflection amplitude. It depends on the way it's measured.
Okay.
So yeah, it kind of gives you an idea of the phase domains.
Thank you. So this model is called Landau-Ginzburg dimensional theory. So this is directly from the thermodynamics. So you think about this energy as polynomial of G. And if the alpha is less than 0, so you will get this double wave energy landscape. So if you take the derivative of G with respect to this P, so you get, and rewrite this, you get a relationship between electric field and the polarization. So if you plot this equation, you can get an S-shaped curve. So it's inside this S-shaped curve. And at first glance, so you cannot get hysteresis. So what happens that between this curve from point A to point B, this region corresponds to so-called negative capacitance region. If you think about this P and E, the slope is negative. So this region is not stable, so you cannot actually measure this. So as a result, what happens at point B, you will jump to point D. And if you're at point A, you will fall to this point C. So that's how to get the counterclockwise hysteresis loop in the ferroelectrics.
So can you say again why you cannot get negative?
Because this region is unstable, so you cannot actually directly measure this. So you think about like negative dielectric constant is like you cannot just measure this with like a CV meter or this. If that helps you. Or
Can we tell that from the thermodynamic free energy diagram?
so yeah, I'll talk about this with next slide. So it's like this. So if you plot this energy landscape equation, so as E equals 0, so you have this double energy landscape, and your initial state is P is as one of the, let's say it's in the left valley. So the region corresponding to negative capacitance is this region here, because the second derivative is negative in this region. So that this corresponds to C equals negative. So if you apply the electric field, so this entrance field gets tilted. So now this P will move to this Q point here. But this is a new minima for the system. So if you further increase the electric field, so there's no longer second minima, so there's only one global minima. As a result, this ball will fall into this global minima, and as it falls, it will travel through this negative capacitance region. So it's like you cannot really measure this.
Sorry, I have another question. Is it you cannot measure this, or is it?
No, it's like if you
transition
just
state
more.
depends?
So there are ways to measure this. It's like not direct ways. If you think, so typically when you measure capacitance of capacitor, so you can use like a CV meter, but like with CV meter you cannot measure this negative capacitance directly. So there's other methods to extract this region. So this part is done by the advisor. So he actually measured the negative capacitance with some of the methods. So you can go to look at this paper, or I can explain here if you want.
We can discuss later.
Okay.
It's really interesting.
Okay, sure. So this is how a typical PE loop look like for PZT. So there are a few important points on this PE loop. The first one is this saturation polarization. So that's the maximum polarization you can get. So the second one is the relative polarization, which is the p-value at which E is 0. So for memory applications, we care about these values. And the last one is the coercive field, which is the electric field when the polarization is 0. So these 2 points here. So in the PDT, there's polycrystalline grain structures. Inside each grain, there are domain structures. So between each domain, there's what's so-called a domain wall. So this domain wall can move under electric field. So the domain wall forms to reduce the first one is to reduce the electrical depolarization energy. So as you can see here, if it's just one domain, you have one electric field. If you have multi-domains, you can reduce the energy associated with the depolarization. and also reduce energy of strain. So, but there's energy associated with the domain wall itself. So you cannot have too many domains. So this tells us there's an optimal size for each domain. So the switching can be understood as nucleation and growth. So if you take a ferroelectric, so assume it's initially it's pointing upward. So then you apply an electric field that's pointing downward. So what happens is that initially you have this nucleation. So this nucleation, the nucleation happens because there are defects in the material. So these defects act as a nucleation site for the nucleation to occur. Then what happens is that this domain will grow vertically to reach the bottom and top electrode. After that, it will grow laterally to expand to fill this space. And if once the entire space is filled, the switching is complete. So this nucleation and growth process are modeled by this what's so-called KAI model. So the essence of this model is this equation here. This T0 is the characteristic time, and this N is the geometric growth dimensionality. So typically for circular domains we use 2. So this text just describes what I have described with this nucleation and growth. So if you plot this, you can see that it's always reach 1. But if you compare this model with the experimental data, you can see that in this t less than 10 to the 5th second, the model fits the data pretty well. So after that, it diverges. So there's a problem with this KAI model. So this KAI model gives good description of the switching dynamics for ferroelectric single crystals and some of the epitaxial thin films, but it has problem when describing these polycrystalline fields. So now I'll introduce the other model called the NLS model. So the problem with the KAI model is that the domains can grow without a restriction. So that means even if you have one nucleus, so you can still switch the entire sample. So this is not true from the experimental perspective, because switching in one region may not lead to switching in other regions. So that's why this NLS model is proposed. So in the NLS models, the film is treated, is consisted of elementary regions. And switching is the switching time for each region is the waiting time for the first nucleation to occur in this region. And in this model, we neglect the domain wall movement, the time for domain wall to move in this region. And this waiting time is distributed across all the elementary regions. So this is the mathematical description for this model. So this P is the fraction of domain that is switched. This P is the distribution function. So they set this tau min and tau max to be the upper and lower limit for the first nucleation to occur in the domain. And these values are voltage dependent. So as you can see here, this model fits the experimental data better than the previous one. And so this plot shows the tau min and tau max and how this is fitted by this relationship here. So now I'll talk about the domain wall movement. So as t equals 0, there's a clear definition of critical field EC0, where the switching will, the domain wall movement will start. For electric field greater than this EC0, the pinning and depinning transition occurs. And the velocity is described by this equation here. And if the E is much larger than EC naught, so you are in this flow region. In this region, the velocity is proportional to the electric field. So at finite temperature, however, you don't have a clear definition of EC naught because the thermal energy will smooth out this transition. So as a result, even at electric field lower than this EC naught, you still have some of the domain movement, and the velocity is described by this equation here. And this figure shows the fitted curve for this equation. Here I'm showing the domain size as a function of right voltage and right time. So as you can see here, the domain size is pretty linear with the writing voltage for different thickness of PZT samples. And in the case of writing time, it's linear with the log of time. Also notice that below a certain time, the domain saturates at like around 20 nanometer. So this is due to the size of the AFMT. That's the resolution you can get from this study. So endurance is very important for memory applications. Here I'm showing the PV loop before and after the fatigue test. So in the fatigue test, what you do is that you apply square bipolar pulses to the material. So we can see that after 3 times 10 to the 9 cycles, there's degradation in the PR value and increase in the critical field. And fatigue is due to the oxygen vacancy formation, oxygen vacancy accumulation, second phase formation, domain wall, pinning, and charge trapping issues. We will talk about this in detail when we talk about Hafnium oxide. So also, you can see here, if you use different electrode, so if you have a metal electrode, the endurance cycle is much less than if you use this conductive oxide electrode. The reason for this is that this oxide electrode allows oxygen vacancy to cross this electrode ferroelectric interface. So the downside for using this type of electrode is this leads to problems such as leakage and retention issues. So here is the scaling of PZT films. As you can see here, around 500 nanometer to 1 micron, the dielectric constant is pretty constant. It's not changing too much, but below 500 nanometer, it's decreased pretty fast. And this phenomenon might due to the what's so-called substrate clamping effect, where the domain motion is limited. So now I'll talk about this CMOS compatible ferroelectric material, doped hafnium oxide. So if you anneal this sample without the top penetrator layer, this material will crystallize and form this monoclinic or tetragonal phase, which is not ferroelectric. So if you made a CV, you only get a flat CV here. So if you deposit the metal layer, top penetrator layer before doing the annealing, you will crystallize this material in this orthorhombic phase, which is the correct phase for ferroelectrics. So then you can get this voltage-dependent capacitance enhancement. So the discovery of ferroelectricity was purely an accident. So a German memory company called Piezoelectric, so in 2006, they tried to develop their electrical materials for DRAM applications with Hafnium oxide and zirconium oxide. So they found out that with certain concentration of silicon, they can get this voltage-dependent CV. This is not reported before. So unfortunately, this company went bankrupt in 2009 because the DRAM price is very low in 2008. So then the NAM Lab and Global Foundry takes this material and continues to do research. So you will see that there's a lot of paper published by NAM Lab and Global Foundry.
Ferroelectric characteristics not only showing on PZT structure.
Yeah. Yeah, so there's a lot of materials. So this one is the CMOS compatible material, so it's very important because now we can make transistors out of this with like advanced technology node. The PZT is not CMOS compatible and it contains lead, so there's issues with that, and also there's scaling issues with that. We'll talk about, when we go to device, we'll talk about the FERAM is stopped at 130 nanometer technology node because it's not CMOS compatible. But with FEFET, we can make it with 22 nanometer technology node.
So does this ferroelectric structure also have similar?
Yeah, similar.
Changing structure?
Yeah.
So at least for PZT, you're storing the memory in the bit in the polarization stage, right?
Yeah.
So how do you read that? Like, is it through IV? Like, how do you?
Yeah. We'll talk about FERAM, then you can know how this works. So after we discovered the silicon doped Hafnium oxide is ferroelectrics, so people tried different dopants and found out, okay, we can make Hafnium oxide ferroelectric with different dopants. And even with pure Hafnium oxide, we can somehow get ferroelectricity out of that. So compared with PZT, this critical field EC value is about 10 times larger because we can make this Hafnium oxide field about 10 nanometers thick. So for the PZT, it's roughly 100 nanometers thick. So that's why we can have like EC value 10 times larger. And also notice that this lancing dope one, this one has the highest PR value. But this result is not reproduced, cannot be reproduced later. So in this slide, I'm showing how this the polarization value depends on the temperature. So in general, if you go to lower temperature, the PR value increases for different types of dopants. And this is because the phase transition from tetrahedral to orthonomic phase with decreasing temperature. And this property also implies that this Hafnium oxide material is good for memory applications at low temperature.